So hello everyone, welcome to Group 2's demonstration video of our laser beam profiler for measuring beam diameter and M² quality. Our team includes Matthew Boyles, Bryce McIntosh, myself Jasenia Forney, and Justin Oriana. Our sponsor is CMS Laser. So we'll be discussing the system design, some key engineering specifications, and the overall functionality demonstration at the end. Here's a quick overview of our device. We created a portable device that measures the diameter and M² beam quality of high-power CW and pulsed laser beams. Optical setup includes 2 alignment irises, an internal optical attenuator, a removable focusing lens, and an optional second lens. A camera module attached to a translation rail and stepper motor moves the camera along the focus of the beam. A custom PCB communicates with the Raspberry Pi and stepper motor. The Raspberry Pi manages the capturing and transfer data to the client, and then the device is controlled with a graphical user interface on a laptop or desktop computer. So here lists our system specifications, and some important things to note include that we need to measure the M² and beam diameter in under 30 minutes with a measurement accuracy of greater than 75%.
In order for the device to be usable, it must deliver results in a reasonable amount of time. The specification was set to 30 minutes per M² measurement to allow for flexibility in the design. One capture is able to be taken, demosaic, transferred over the network, and measured every 42 seconds on average. Given at least 10 beam captures and 1 background capture are needed, this puts the total measurement time at approximately 7 minutes and 32 seconds total, which is within our specification.
In this section, we verified that our device can measure beam diameter and M² quality. A knife edge measurement was done versus our device using a green 532 nanometer laser. The measurements were 1.5% accurate between each other. Here we have our program viewer, the data points and curve fit. At the bottom, we have the M² minimum waist, relay length, and divergence angle calculated and presented for both the X and Y axis. Here we test the accuracy of our measurements to verify that they are greater than 75%. To do this, we use the same optical setup for the test and verification shown here. We used the helium neon laser, a 5x beam expander, and 2 adjustable mirrors. For our test, we placed the same focusing lens at 55 centimeters from the last mirror of the test laser, shown on the top. Below, we can see our device with the lens at the same location from the last laser at 75 centimeters. This is to keep the beam diameter consistent for both measurements. The knife edge was done at 2 locations from the lens shown here, one at 100 millimeters and the other at 160 millimeters. The data was plotted and the divergence angle was calculated to be 6.138 milliradians. The waist versus focal position for our device is plotted here. A divergence angle of 6.5 milliradians was measured from our curve fit of the measured data with an M² of 0.96 plus or minus 0.157. Our M² value 1, but we did an error analysis to find the cause. We found that we are limited by the camera sensor when capturing at each location, plus or minus 2 pixels. This creates an uncertainty with the M², causing it to fall below 1. Although the plus or minus will be higher than 1. Since our divergence angles are within 6% of each other, this confirms that the data may have been shifted up or down, causing the M² to be off.
This is our final PCB circuit design. You can see here a 12-volt DC jack that would bring the 12 volts from our battery supply down through the buck converter. The buck converter down regulating to 3.3 volts across our MCU and TMC 2208, which would allow us to drive our motor, the NEMA 17. and these are our programmable pins from the Raspberry Pi to the MCU. However, in testing, this circuit did not operate as intended, as the 12 volts was not being regulated down to 3.3 volts. Instead, we were seeing 12 volts across the board. Therefore, we assume that this buck converter was not operating as it should be. Therefore, we had to change tact and create our own circuit in the lab. This design circuit using the voltage regulator LM338 was created and tested.
Battery. Now power is on. We're going to measure across our load resistor. And now we see 3.3 volts.
So, as we discussed, our regulator was not working properly due to the resistors the manufacturer placed for the voltage divider being incorrect. So we had to hand solder our board instead. So as seen here, you can see the microcontroller board on the left, then the driver board on the right, and then the voltage regulator is kind of under all those cables. And the battery is under the Raspberry Pi, and they all connect to each other to move the motor and perform the measurements.
We will now discuss the functional parts of our device. This device was designed to be portable, allowing the user to use it in any laser setup they have. Once placed in the beam path, the user can start to align the laser into the system, and the device will be ready to go. Here I am aligning the laser into the system with 2 adjustable mirrors. Looking inside the device, we see that the beam will pass through an aperture to a wedge, and then pass to another wedge, and finally to the focusing lens. A beam block will block the beam, and 3 ND filters can be pulled into the line of the beam. The beam will then pass through the lens and hit the camera sensor. The 3 ND filters can be pulled from the outside to activate them and are labeled with the optical densities. A beam blocker can be pulled up to block the beam from the sensor.
After aligning the beam into the system, the user opens up the user interface. They enter the wavelength of the beam in nanometers, in this case is 632.8. They select the width definition, in this case 1/e squared. And they should perform a background capture. They raise the beam block in the device to block the beam from the camera and select the background button at the bottom of the screen. The device will then capture a background. For time's sake, I will skip this part because it will take 40 seconds to receive the capture. Now that the background image is being received, the user interface will let the user know that it's received, and we can perform a capture. Again, the capture will take approximately 40 seconds. And after it's finished receiving, you can see the beam displayed on the left with its parameters, location, waist in the X, waist in the Y, and you can select crop and grid to display a grid or crop the image around the beam.